I want to start with a big picture, which is going to be kind of vague. So don't feel like this is something that has to make complete sense. We'll be drilling down and making this much more precise through several examples later on. So we're talking about system, program, protocol security. And we've got a little picture here where we've got two components, an honest one and a malicious one, that are interacting in some way, maybe trying to cooperate, but as the name suggests, the malicious one is maybe trying to trick the honest one, learn things it shouldn't learn, convince the honest part of something that it shouldn't be able to convince it of. They have clients, and so indirectly, the client of the malicious one may be gaining some advantage of the client of the honest one. And we're going to talk about how we could define security in such a setting. But first, let me talk about several ways that we could try to enforce security. So the first is using cryptographic mechanisms. And so what's the basis for getting security out of cryptography? Hopefully good randomness is a big part of this. Hopefully intractable mathematical problems, which quantum computing may turn on its head. So factoring numbers or whatever might turn into something that wasn't hard, depending upon the kind of computer you have. And then finally, unpredictable complexity, as is used like in hash functions. And that's what I've illustrated at the bottom. So cryptographic hashing is something that's completely deterministic. It's some actual code. And like in any hashing, you expect to have collisions, but because you're going from a bigger set to a smaller set. But in cryptographic hashing, if X hashes to Y, as illustrated on the left side, it needs to be really hard to find something else that hashes to the same thing. If you have some result here, finding something, excuse me, that hashes to it should be hard. But hard in what sense? That's the thing that's kind of striking. So it's a deterministic algorithm. And so once you know a collision, then it's kind of game over for that cryptographic hashing algorithm. It's not hard in a complexity theory sense, but we live with these unpredictable complexity algorithms as long as they're good. Once people break them, then we move on to something else. So that's one way. Another is through PL security. So we can have unforgeable references to objects on the heap. You can't make them up out of something. Either you know it or you don't. Data abstraction. You can use these to implement things like dynamic information flow control and access control, which I think Steve Chong will be talking about some of this. Another possibility is to have resource managers, like an operating system that hold various objects, and the clients here can refer to these objects via descriptors, which are forgeable. They're just small integers, maybe. But the point is that this client's descriptors don't mean anything at all to the other descriptor because they're indexing tables that are held by the resource manager. So here are several ways that we could try to obtain security. And there are others. You could use them in conjunction, some arbitrary combination of these things. But how do we define security? So we've got this picture here. One answer is to employ the real ideal paradigm from theoretical crypto. And so what we're going to do is take this real system and turn it into the diagram that's on the left here. But instead of having the two different components talk to their clients, they're going to talk to an adversary that plays both roles. So the adversary over here is sending inputs to the honest part, consuming the outputs, and similarly for the malicious part. The idea is the adversary is the most general kind of combination of clients. It knows what both clients are doing, or it can know. So it's a general attacker. That's the real system. Then we have an ideal system that's supposed to be secure by construction And its cornerstone is this ideal functionality, which prescribes the honest behavior. And on the malicious side, it leaks certain information to what's called a simulator. Inside the simulator, we have the malicious component that's sandboxed. And you can think, if you anthropomorphize, which I like to do, and Dijkstra hates, yeah, we can think that M has no idea that it's inside the simulator. It thinks it's talking to H. It's actually talking to part of the simulator. And so it's sandbox, it's protected from the ideal functionality by what's allowed to flow across this channel here. And the idea is the simulator is then supposed to convince the adversary or try to convince the adversary that it's actually in the real world, that it's actually talking directly to M, but the simulator can only work with the information that flows from here to there. So the M here, we can say exactly what damage M could possibly do by what can flow from the honest party's inputs to here, what control comes back this other direction. Just a second. And but what we're going to want when defining security is to say that the adversary can't tell these two different worlds apart. I'm going to drill down a little bit more on that in a second, but there was a question.
How would you use this to define, for example, security of a hash?
Yeah, so I don't want to go into any examples right now, so we'll see a number of examples as we go on. Okay, so what does it mean? So the idea is this is supposed to be secure by construction. If the adversary can't tell the two worlds apart, then we think, okay, this is secure as well. But you might be wondering, what does it mean to tell them apart? In particular, can you run both of these worlds sort of step by step and compare the answers? And the answer is no, that's not going to work out well in the context, at least, of probabilistic semantics. So instead, what we do is we have the adversary do an experiment on one side or the other side, and at the end of the day, return a Boolean judgment. And what we want is that for security, is that in the cryptographic case, the probability that the adversary returns true is close. We'd like it to be exactly the same. In a typical crypto setting, we can't obtain that, but we could say that the absolute value of the probabilities that we get true in the two worlds is very, very small, is negligible. And so that's going to be our goal. In a non-probabilistic setting, we could just say that we want the Boolean to be the same. But the point of this is that the adversary can experiment individually with one of these worlds. After it's seen enough, it returns true or false. It doesn't get to run them in parallel, so it has to try to learn what it needs to learn. And so if you're the adversary, you should be maybe trying to return true to say it's the real world, and false to say it's the ideal world. You know, that would be your goal. But we're going to try to make that very hard for the adversary to pull off. And if we manage to prove that the adversary can only tell them apart with negligible probability, then we'll say that we have security in the real world, because in the ideal world, we have it by construction. So that's the really big picture. And I appreciate that we haven't gone into any details about what the system does. And that's why we're going to dig deeper with particular examples. Okay. So in these lectures, we're going to consider 3 applications of the real ideal paradigm. In the form just presented, it's also known as simulation-based security, because there's this simulator, but there are forms of the real ideal paradigm that don't involve a simulator, which we'll also see. 2 of them are going to be related to the EasyCrypt proof assistant, which I'll tell you about in a minute. The third is going to be situated in 2 functional languages. So concurrent Haskell plus this LIO, Dynamic Information Flow Control Library, concurrent ML plus homegrown access control. And my big thesis is that the real ideal paradigm is applicable much more generally than just in crypto. And so I'd like you to, as you go about your PL lives in the future, to keep in mind that maybe this is a way of trying to define security. So let's talk a little bit about EasyCrypt. How many people already know anything at all about it? A few people, cool. So it's an interactive proof assistant for reasoning about probabilistic imperative programs, including ones involving black box code that might represent an adversary, which will quantify over in proofs. So for all adversaries, something or other is true. Its object programming language has statements, conditionals, while loops, ordinary assignments, random assignments from distributions. So a lot like flip. But more general, kind of confusingly, we can do choices from sub-distributions where the sum of the weights doesn't come all the way up to 1. And if you're unlucky enough to hit a gap, that would mean that the program would just die. The reason that we have these in EasyCrypt is that non-termination is one of the ways that we can end up with not summing to 1. But in what I'm going to be talking about, we'll always work with distributions. We're always going to work with programs that terminate with probability 1. We also have modules consisting of procedures plus persistent variables, so state at the module level, possibly parameterized by black box code. And EasyCrypt has 4 program logics, which we'll see a little bit of. There's a HOR logic for partial correctness, a probabilistic HOR logic for bounding the probability that procedures terminate with some predicate holding on the resulting memory, with some event holding, we say. A probabilistic relational HOR logic for relational reasoning, which is going to be huge in this real ideal way, because you can think we're comparing a real world and an ideal world. That sounds like relational reasoning. And in fact, that's the backbone of how you do proofs in crypto. And a classical higher order ambient logic for doing ordinary math and connecting judgments from the other logics. And I'm going to show you a simple example, a sketch of a simple example of how we can do all of these things. Let's see, okay? It's not dependently typed, so it's a higher order logic, classical higher order logic. Proofs of lemmas are carried out using tactics in a style that's very similar to Coq, specifically SS reflect, if you know about that. You can, in a theory, you can combine a bunch of definitions, module definitions, sequences of lemmas. They can have parameters, and you can clone those parameters, and then any axioms that you stated involving the parameters, you'll have to prove as lemmas. So that was a really high-level overview of EasyCrypt, but now let's look at an example. So we have 2 modules, M and N here. They both have a procedure called F that takes no arguments, no parameters. It returns a Boolean. And this is going to kind of take us back to what we had in Steve's lecture. So in the first one, what we're doing is we are sampling a random Boolean. And confusingly, even though true and false are the Booleans, the way that we talk about the uniform distribution on the Booleans is this way that crypto people would like, because they think of true and false as being 1 and 0. This is the name for the uniform distribution on the Booleans. This says sample a random Boolean and return it. This one is saying sample B1, sample B2, and then return their exclusive OR. Anyone know offhand whether the probabilities that these 2 procedures return true, are they going to be the same? Turns out the answer is yes, but we can see why. So let's think. How do we define the semantics for this? Well, there is in fact the probability monad in the background, but we can picture how this works by a tree. So this dovetails nicely with what Stephen was talking about. So let's think about the semantics of the second procedure here. So n.f. So it's doing these two choices. So here we're doing the first choice. With probability 1/2, we end up either with true or false. If we're on this branch here, we're choosing B2. Again, probability 1/2. And so when we end up over here, we multiply these two probabilities, we get 0.25. And then why is this false? Because it's the exclusive OR of true in itself, which turns out to be false. Here we've got exclusive OR of true and false, which is true, false and true, which is true, false and false, which is false. And then if you look here, the probability that we get true out is 1/2. Probability that we get false out is 1/2. And so pretty obviously, right, if we go back to here, the probability that this returns true is 1/2. And so pictorially, we now have a proof that these two procedures return true with exactly the same probability. Okay, so but how does this look in the logics of EasyCrypt? Well, what you can do is you can state this lemma here, that running m.f with some starting memory. Why is the memory relevant? If we go back for a second, the memory would only be relevant if we had module level variables, which we don't. So, so actually the initial memory here is kind of irrelevant. But then this is saying the probability that if we start m.f up with this initial memory, that it terminates in a memory in which the result field, so the memory has, in an output memory has the result as one of its parts, that the result field is true, is the way that you should read this. So the probability that running m.f from some starting memory, which is a parameter to the lemma, returns true is exactly 1/2. This %r stuff, you can guess, it's turning integers into real numbers. So we have to do that before we do the division here. So this is something that we can prove. In the supplementary material I've made available, you can see the proof of this. I'm not going to show you it in the lecture today. So let's just assume that we managed to do that, because that was the easy one, right? We're just flipping one coin and returning the result. But then we can go on and do a relational judgment, a PRHL, probabilistic relational horologic judgment, that looks like this. It's a quadruple. So we've got m.f and n.f, the two procedures. And then we have a precondition and a postcondition, which are now relations on pairs of memories, although the way that we express them is by using tags. So here, true is likes any pair of memories, so it's not saying anything at all about them. But here, what about this one? It's saying this is going to like a pair of memories where the result of the first is the same as the result of the second, where the result is this Boolean. So we're using these tags to say which memory we're talking about. Now, the thing that's kind of weird here is that this is saying, well, we start with a pair of memories that true likes, so true likes any pair of memories, start with a pair of memories, feed them in to m.f and n.f. What we get when we run those are probability distributions on a distribution on memories. So, so what memories can we end up with what probabilities? But this is just a postcondition on pairs of memories. So there's a disconnect there, and we have to understand formally how we square that circle. So in general, we have some quadruple that's like this. And incidentally, the tilde here and the double arrow, they're just syntax. So you should just think of this as there's a procedure, another procedure, a precondition on memories, a postcondition on memories. To understand formally what this means, we have to take this postcondition here, Q, on pairs of memories and lift it to work on distributions of memories, which are going to be produced by m.f and n.g. And that's done using an idea called probabilistic relational coupling. It's not hard to go into the details of, but the kind of remarkable thing is you don't really use it directly when you're doing proofs in EasyCrypt. And so I'm not going to do that detour, because in practice we can think and work a lot more informally. And I'm going to try to give you an idea how we can do that, for instance, on this next slide. Temperature warning.
It's okay.
It should be
Okay,
fine, don't worry.
okay. So I shouldn't panic. Okay. So here's the way that we can work with this. Suppose we've proven this judgment here, PRHL judgment. So the no constraints on the initial memories. This is the post condition. And suppose what we really wanted to do was prove this, that the probability of running m.f from memory m terminating with a memory that this predicate on memories E likes is the same as running n.g and having a predicate, an event F. So this is maybe what we really want to know. Well, if we can prove in the ambient higher order logic that this post condition, which we should think of again as a relation on pairs of memories, the result memories, including this result field, suppose that implies the if and only if of these two events, where I've decorated all the variables in the result field of E to say, well, interpret them in memory 1, and for F, memory 2. So suppose we prove this, and we prove that in the ambient logic, then that lets us conclude this. If this was a left to right implication, then this would turn into not equality, but what do you think? Someone make a guess? Sorry? Yeah, less than or equals to. So, so if we know that just E in 1 implies F in 2, then that's going to tell us the probability that running m.f from the memory M results in a final memory that E likes will be less than or equal to the probability of this. So we can read off, we can do this work. We can combine it with a little bit of ambient logic reasoning, and then we can get these facts about the probabilities of running procedures resulting in a final memory that satisfies some event. We can get that as a corollary. Yes? Well, yeah, so again, this is saying, so E here, what can it talk about? It can talk about the module level variables of M. It can also talk about the result of this procedure. And similarly, F over here. But when we put them into one relational formula, then we have to be able to talk about which memory they're from. So that's what the 1 is saying, well, look at the memory of m.f, and the 2 is saying look in the memory of n.g.
So numbers are like an offset.
They're just telling us whether to look at the left memory or the right memory. Because if this is saying res, for instance, so let's in fact look at this. So suppose we prove this, which relates now to the example that I showed you with flipping coins and exclusive OR. So if we prove this, so this is something that's equivalent to saying the result of m.f holds if and only if the result of n.f. That's how we should think about this. And so that lets us say, well, we can go from here to here. So this event is copied there, this event is copied there, but in here, they have to have these tags to say, well, the result of the left computation, the result of the right computation. Yes?
So how is it defined? Is it existentially quantifying over a coupling?
Over what?
Over a probabilistic coupling?
So it's defined using probabilistic coupling, but I don't want to go into the details of that. I mean, so we should think roughly that here we take a pair of memories that true like, so any pair of memories, we run m.f on the first, n.f on the second, we get a pair of distributions on memories, and then we have to take this and lift it to apply on those memory distributions. And I'm not going to tell you the details of that.
But to prove it, we can construct the one we want.
Yes, I mean, once and for all, you prove the soundness of the logic, and then you can just use it. But my point is that we don't have to think, we never have to think when doing an easy crypt proof in terms of that semantics.
Okay, but maybe a related question to this, could I also prove on the same function that res1 is not equal to res2 by taking basically the opposite?
Yeah, yes, you could. Yeah. Okay, and then, right, so we have this, but then we already supposed we'd prove that this probability is a half, and then that lets us show that the harder one, the one that we showed by that diagram, returns true with a half as well. So we can do some reasoning about m.f, which is easier. We can do some relational reasoning, and then from here we can get this, and then we can say, well, n.f returns true with probability exactly a half as well. Okay. Well, let me show you the interesting part of the relational proof. So here we are trying to prove this at the point where we've already chosen v1 in n.f. So we've made the first choice in n.f. We have this goal here. So here's the precondition. We don't know anything at all about v1 because it could have been true, it could have been false. Here is the program on m.f. Here's the rest of the program in n.f. So choosing v2. And here is the postcondition, that the results are equal. Well, the result on the left side is this. The result on the right side is take v1 and v2 and exclusive OR them. And note the tags, right? We're talking about the left memory, the right memory. Now, what we want to do is use a tactic, program tactic, that pushes these two assignments into the postcondition. And if we do that in the default way, what we're going to end up with is a universally quantified variable in this position and the same one in that position. And then this is going to be something that we can't possibly prove. Because if the value of v1 in memory 2 is true, then this is like negation. So what we have to do is use instead the RAND tactic with an isomorphism on distributions. So this is the isomorphism that, given a Boolean, exclusive ORs it with the value of v1 in memory 2. So take in a Boolean and exclusive OR it with this thing that's now fixed. That's this function. We can give that as the argument to the RAND tactic. And what it does is it pushes these two random assignments into the postcondition where they're kind of down here, we'll see. This first part here is saying that we have to prove that every element in the support of the Booleans, which is actually everything. So every Boolean has the property that if you do this function twice, then you get back to where you started from. And that's something that the exclusive OR rules say that these are going to cancel out, so that'll be fine. We also have that if you start from the left, you take anything in the support, any Boolean, that running it from the left cancels out. So that's the isomorphism part. Why do we have to do both? Because in general, you can have a pair of maps, one that goes from the left to the right, another one that comes from the right to the left. But don't worry about that. The interesting thing, apart from this work here that we have to do to make sure that we're kosher, is what happened to the post condition. So here, if this is the original post condition, so now we've still got this that's here, but the left choice is BL. The right choice, so the value of B2 here is now not BL, not this universally quantified variable, but the result of applying this isomorphism to BL. And we chose this because if you look at this, these will cancel out and we'll just end up with BL is equal to BL. So at a fast kind of pace, this is an example of the kind of relational reasoning that you can do. Is this sound? Well, there's a proof involving relational coupling that proves that this is actually sound as long as, as long as we do this work here, then this is sound reasoning. Yes?
I just want to make sure I understand. So is the Wren tactic doing something different than what you could normally do in the logic of the proof assistant, or is it some collection of things that you could do by applying other mechanisms?
It actually, so EasyCrypt is not embedded in some other proof assistant. So there is actually this PRHL logic has certain tactics, and RAND is one of them. So this is something it's built into it, but there's a paper and pencil proof that relative to the validity, which involves relational coupling, that this is sound. Good question. Okay, so right, I'm not going to actually do a bunch of proofs at this level. Mostly, I'm going to be talking more big picture in the rest of my lectures. I might do some live coding. I really don't know time-wise, but I'm happy to answer questions. And I'll post a few simple exercises that are sort of like the one that I just did if you want to dive into this. And you can, of course, ask me questions about it. Okay. So let's start talking about cryptographic security. So cryptographic schemes like encryption and protocols like key exchange can be specified at a high level in EasyCrypt's programming language. They make use of randomness. In reality, of course, we have to implement randomness, which makes things a lot more messy and imperfect. We're working with pseudo-randomness. That's not something that we're going to do in these lectures. So we're going to work at this ivory tower, lovely level where we can specify things and think we have real distributions that we can just sample from. There is work like Jasmine, which is related to EasyCrypt, for formally connecting high-level EasyCrypt code with efficient low-level implementations. Okay, first example, we're going to see 3 examples in these lectures. We'll start example 1 today, and then we'll finish it next time and start example 2, and so on. So we're going to see how we can define symmetric encryption out of randomness plus a pseudo-random function, a PRF. If you don't know what that is, there's no problem. We'll come to that. Specify security for this scheme. It's called indistinguishability under chosen plain text attack, or INCPA. Prove security of the scheme using a reduction to the security of the PRF. We're going to here employ a form of the real ideal paradigm that doesn't use a simulator. In fact, a couple ways, but the top level security theorem isn't actually going to look like it's real ideal at all. It's going to use what's called an indistinguishability game. But I think it's still useful to think of the building blocks that we're going to use being real ideal. And the code you can find on GitHub, and we'll post these slides, of course. Okay, so let's see. Okay, time-wise. Okay, so So our treatment of symmetric encryption is parameterized by 3 types. A type of keys, encryption keys, which are bit strings of length keylen bits. So this is a tunable parameter here. Text is bit strings of length textlen bits. And then cipher is the result, ciphertext, but it depends upon the scheme what these are going to be. So we're going to be encrypting plain text using keys, but what the ciphertexts are is something we're going to drill down and explain a little bit later today. An encryption scheme is an implementation of this module interface. So it has a procedure for generating a key, for encrypting a plain text with a key, getting a ciphertext, for decrypting a ciphertext using a key, and getting back to a plain text. It's supposed to be stateless. So there are these 3 procedures in a module, but with no global variables in that module. And what do we want for correctness? Well, we want that if we call, so correct is a module that's parameterized by some encryption scheme. The encryption scheme we're going to say is correct if running its main procedure with some arbitrary x will return true with probability 1. And what does main do? It generates a key, stores it in k, it encrypts x with k, gets the ciphertext, it decrypts the ciphertext with the same key, gets y, and it compares that x and y are equal. So we want that this always returns true to be correctness. But we're working in this probabilistic setting, and so everything has to be conditioned on with probability something. Here we want it with probability 1. Okay, so that's what we want for correctness.
Just curious, does this apply to asymmetric keys?
So definitions would be different there. I mean, you can do that in EasyCrypt as well, asymmetric encryption, but that's not what we're going to do in our example. Yes?
Is this assuming that your encryption scheme is not trivial, like it's not just encrypting everything to the same?
So the question is, are we making any assumptions about the encryption scheme yet? And well, so we could very well have a stupid encryption scheme that just used the ciphertext to be the plain text.
Yes.
That would be correct, but it's not going to be secure. And we haven't said yet what security means.
Is it probabilistic encryption or?
Oh, well, we'll come to that, but the answer is going to be yes. And in fact, the answer is going to be that it has to be, but let's come back to that. So good question. So is encryption probabilistic? Everything is potentially probabilistic in EasyCrypt. There's in fact no way of saying that it's definitely not. Okay, so then how do we define security? Because as you pointed out, we want something that's hard to break. How do we say what security means? We're going to use a game called in CPA. To build up to that, we need some concepts. So we need the concept of an encryption oracle. And so an encryption oracle implements these 4 procedures, a way of initializing itself, which normally generates an encryption key, which it stores within itself. And then a way of encrypting, 3 ways of encrypting a plain text, getting a ciphertext. This is the one that the adversary will use before it picks its pair of plain texts. This is the one that the game uses. This is the one that the adversary uses after it's given the ciphertext and it's trying to figure out whether the ciphertext came from the first plain text or the second. If you haven't seen this before, that probably seemed completely confusing. So hold on to these doubts, and we'll explain this once we see the game. Here is the standard way of implementing an encryption oracle out of an encryption scheme. So we call this module with whatever scheme we had in mind, hopefully one that's good. And then what does it provide? Well, it has 3 module level variables, the key, and then 2 counters. And init, in fact, generates a key using the keygen procedure of whatever the scheme is that we plugged in here, and we store it as a module level variable. These counters are both set to 0. So you're probably wondering, what do the counters do? So here we can see in enc_pre. So enc_pre, when called with the plain text x, it says, well, if the counter hasn't reached this limit, which is a tunable parameter, then we will increment the counter. We will encrypt x using the key, which is this module level variable that's here. And that'll be the ciphertext, which we're going to return. If we reach the limit, though, we're going to start just returning some default result. Doesn't matter what this is. It's just some definite thing. So what we can infer here is that enc_pre will do encryption using the key that was generated and stored by the initialization procedure until we hit this limit. And then it just starts returning some default result. genc, games encryption, does encryption using the stored key with no constraints. Enc_post does what enc_pre does, but with a different counter and a different limit. So here are counter post and limit post. So far, just to recap, we have this encryption oracle that's built out of whatever encryption scheme that we're working with, and it provides these 4 procedures. It knows inside it as persistent state the key and these 2 counters, which both start out at 0. Okay, so now what's an adversary that attacks the encryption scheme? Yes?
Sorry, I wanted to go back for a second because I know a little about cryptography, but I forgot how the game works. So can you remind me what the pre?
We're gonna see the game in a minute. So the problem with pedagogically, right? The problem with this is if I show you the game before showing you these definitions, then you think, well, you know, what's going on? So it's like it's a cyclic thing that once we get to the game, then we can come back to this again if we need to. Excellent question. Yes?
So my question is, how is the encryption oracle different from the encryption implementation?
So the encryption oracle is built out of the encryption scheme, which we haven't seen an example of yet. So it does encryption however the encryption scheme does, but the encryption scheme is stateless, and the encryption oracle is this thing that has the key that was generated by init and these counters within it. So let me go on just a little bit, and then let's take questions. So the adversary is given access to an encryption oracle, and the adversary has 2 procedures called choose and guess. Choose is supposed to return a pair of plain texts, and this says that it's allowed to call the enc_pre procedure of the encryption oracle that it was given access to. Guess is given a ciphertext. It's supposed to return a Boolean. It's allowed to call enc_post. And this Boolean, what's it supposed to be trying to guess? It's supposed to be trying to guess which of its plain texts the game actually encrypted. And so let me show you one more slide, and then we can cycle back and forth until everyone has their concerns addressed. So, right, but to say it again, choose is allowed to call enc_pre. It's not allowed to reinitialize the encryption oracle. It's not allowed to call any other procedure. Guess is allowed to call enc_post. They both have their independent counters, remember. So here, and right, the adversary can be probabilistic. Everything can be probabilistic. So here is the NCPA game. And so this brings this stuff all together. So it's parameterized by an encryption scheme and an adversary. And So what we do is we say, well, take the encryption scheme, build the standard encryption oracle out of it. So that's what EO is. So EO is all of this stuff here, which now knows about the particular encryption scheme that we supply to the INCPA game here. This is an encryption oracle which we give the adversary access to. So A now, all by itself, is the adversary specialized to this particular encryption oracle, which knows about this encryption scheme. And what it has is a main procedure that returns a Boolean. How does it work? It initializes the encryption oracle. It then calls the adversary's choose procedure, inviting it to return a pair of plain texts, x1 and x2. And what we saw was that as the adversary's choose procedure is running, it can call enc_pre as many times as it likes. But remember that when enc_pre runs, it only does something interesting until we get to this limit. After that, it starts returning these boring results. So in other words, when the adversary is trying to figure out, scratching its head, thinking, what's this pair of plain text I'm going to return? It can encrypt anything it likes. It can encrypt x1 and x2 even, which is gets to a question that was asked before. We'll come back to that in a second. Then, okay, the game gets this pair of plain texts. It now flips a coin, generates a random Boolean. If the Boolean is true, then it takes x1 and encrypts it using genc. If the Boolean is false, it takes x2 and encrypts it, and it gets the ciphertext back. Genc does encryption using the stored key that was created by initializing the encryption oracle with no limits. So we have a ciphertext here. We now give that to the guess procedure of the adversary. The adversary now, if we want to be completely formal, it's trying to guess B. So it's going to return a Boolean, and it would like that Boolean to be B. Now, B was used to figure out which of x1 or x2, which came from the adversary, should be encrypted. But technically, if the adversary was foolish and x1 and x2 were equal, then it's really B that's trying to be guessed, because there is no difference between, so it's really B. We should think that the adversary is trying to guess. Right, and so when the guess procedure is called, it can call enc_post. And so it can call this as many times as it likes, which is doing encryption using the actual key that the game used to do the encryption. And so maybe we can, I pose this question on a slide in a second, but let's just handle it right now because people have already brought this up. Why is this just not an impossible problem to solve? So, we're returning a pair of plain text, or why is it, right, sorry, let me try again. This is returning whether the adversary guessed right. So when true comes out of this main procedure, that means that the adversary, that the adversary won. And what we would like to do is prove that the adversary doesn't win more than half the time. We'll come to that in a second. But why is this not just impossible? Because it seems like the adversary can pick these plain texts. It can actually encrypt them and get a pair of ciphertexts. Why can't it just say it's given the ciphertext that was produced here? Why can't it just compare C with the encryptions that it made?
Is it that the adversary has to not win more than half the time at all, or is it about half the time?
Yeah, well, let's come to that in a second. But why, I mean, it seems on the surface like there should be no secure scheme. I mean, that if we don't want the adversary to win more than, much more than half the time, I mean, it seems like it can just come up with x1 and x2. It can encrypt them, get C1 and C2. And then when given C, it can just ask, is C equal to C1 or C2?
Is the issue the choice of key?
The issue is not the choice of key.
It doesn't know the secret key.
It doesn't know the secret key, but remember, it's allowed to experiment with the very same key.
So it can't actually call a decrypt function. So if it wanted to do that, they have to like guess and check, and that's really hard, which is like computationally intractable.
Right, but I think we're missing the main issue here.
Are we required that the encryption key is deterministic?
Yeah, so that's why I said that someone already raised the salient thing here. So the point is that encryption has to be probabilistic if it were deterministic. So if you try to implement encryption in a way that's deterministic, then you can do exactly what I said. If you're the adversary, you can say, okay, I'll encrypt x1 and x2. I'll get C1 and C2. When I'm given C, I can just ask, is it C1? Return true. If it's C2, return false. But the point is that encryption is probabilistic necessarily. And so there is no way of having a secure scheme. I still haven't exactly said what secure means, but I will in just a second, unless encryption is probabilistic. Decryption has to be deterministic because you want to get back to the same answer. But that's the reason that this works.
Can the adversary here call the encryption oracle more than once?
Yes, it can when choose is called. Excellent question. It can call encpri as many times as it likes, but remember that encpri, after some parameter of calls, starts no longer doing anything interesting. And that's going to be important as well. So we don't, there's a reason for these parameters, because when we state security, it's going to be partly a function of limit pre and limit post. So let's see. So let me say, oh, right, this is the picture. So the game calls EO to initialize itself. It then invokes the adversary saying, pick this pair of plaintexts. The adversary keeps calling, can call the encryption oracle on whatever it likes. It gets interesting answers as long as it doesn't, using the real key, saved by EO, as long as we don't exceed the limit. It returns those plaintexts to the game. The game flips a coin, encrypts one of them, gives that back to the adversary, which again can call the encryption oracle in enc post some number of times, getting interesting examples. It then returns a Boolean. And the question is this Boolean the same as the Boolean that determined which of x1 or x2 was encrypted? Okay, so if the value b prime that the adversary returns is independent from the b that was used to decide whether to encrypt x1 or x2, then the adversary will win the game exactly half the time. In other words, if the adversary says, I'm going to be lazy, I'm just going to always return true or false or always return a random Boolean, these are all independent from the b. If we go back, all independent from this b here. And so the probability that it guesses right here will be exactly a half. So the question is, how much better can it do? And we would like to prove that it never can do better at all, but that's not going to be possible. So we want to prove that it can't do much better than win half the time. That's going to depend on the quality of the encryption scheme. The one that just returned, as the ciphertext, the plain text, well, that's going to, not be secure. That the adversary can break that one because encryption was deterministic there. So there it can win all the time, which would be bad. Okay. So an adversary that wins with probability greater than a half can be turned into one that loses with that probability and vice versa. And so it's convenient when proving and stating security to bound the distance between the probability that the adversary wins the game and a half. So we don't want it to be able to do much better. We also don't want it to do much worse because, well, technically that works out better. And if it could do worse, well, we could just flip what it returned and then it could do better. And so what we're going to be doing is proving something like this, that the absolute value of the probability that the adversary wins, that the NCPA game started in an initial memory, but the encryption oracle has global variables, but they're all initialized. So the initial memory is actually not really relevant here. So the probability that true comes out from running the NCPA game minus half, the absolute value of that should be bounded by something. It's going to end up being bounded by something that's a function of the adversary. We'll see why, and some other stuff here. And right, the upper bound could also be, will also, in the scheme that we look at, will also be a function of the number of bits in a plain text and the limits, limit pre and limit post. And don't worry if you don't have any idea why. We haven't come to the encryption scheme yet. We will in a minute. Right. So, why isn't it just impossible to have a secure scheme? Because encryption is probabilistic. If it's not probabilistic, the adversary can always win. What's the rationale for letting the adversary even call enc pre and enc post? Anyone have an idea?
It just gives the attacker more possibilities for attacking our schemes and therefore maybe represents the real world in a better way.
Yeah, so it represents the real world better. Go ahead.
The idea is that an encryption scheme should be secure even if the person trying to break it knows exactly how it works. And this is like a model for that, if I remember correctly.
Yeah, I mean, the way that I think I would expand on what you said, that it models the possibility that the adversary might be able to convince the person that has the key to encrypt certain things. So if you have a key and I'm interacting with you, and to do some protocol, you have to encrypt what I gave you. Then it's modeling that. So it's modeling the fact that the adversary might be able to convince the person that has the key that the adversary doesn't know to encrypt certain things.
Is it possible to define another game where maybe deterministic encryption is secure?
Maybe, but I don't want to try to go there right now. Okay. And why do we limit it? I mean, well, there are two reasons. If we don't limit it, we don't get any kind of reasonable security theorem. But if you have the key and I'm sending you stuff and optionally you're encrypting it, well, you could decide, I'm doing a denial of service attack and you're not going to play games anymore. That you have the key, you can decide how many times you want someone else to be able to influence you to do the encryption. So that's what this is modeling. And it's part of the kind of art of crafting these crypto definitions, figuring out what you're trying to model. Okay. So what I want to do now is show you the scheme that we're going to use. And it's based on a pseudorandom function, which for us is just an operator f with this type. It takes in a key, and then it's a curried function, then it takes in a text value, and based on the key, it transforms it into an answer. So for each key, this is a function from text to text. Keylen is the number of keys, a number of bits in a key, so there are 2 to the keylen of these functions here. And we could try to spell out how f works, but we're going to keep it completely abstract. Think of it as a black box. But how do we talk about when an f is good? We do it using an instance of the real ideal paradigm. So let's see. D text is going to be a distribution on text that's uniform. D key is going to be a distribution on keys that's uniform. Technically, distir can include subdistributions, but we're adding axioms to say that these are the uniform distributions. So if they're textlen bits in a text value, there are 2 to the textlen different possibilities. Each of them has equal weight. So picking a particular, the weight of every text value is 1 over 2 to the textlen. Okay, now we're going to have a concept of a random function module. It has 2 procedures, a init and f. F transforms a text to a text. We're going to implement this in 2 ways, one based on our PRF. So think of this capital F, this function of this type here, as this fixed thing that's in the background. And what this does, init generates a key and stores it, so it can remember it. F just uses that key to transform X. So that's what this one does. So this is based on the actual F. The other one is based on a dynamically expandable map. So it has within it a finite map from text to text, which starts out being empty with init. When you call F with a text value, it says, well, if X is already known about the map, we skip down to here, we look up the value of X and we return it. Otherwise, we generate a random answer Y and we update the map so that X is mapped to Y. So it's memoizing the result. Each time you call F, if either it looks up the answer that it already knows or it generates a random answer for the X, updates the map to memoize that. So if you think about it, as we run F, we could, if computation is no object, we could call F with all of the 2 to the textlen different values, one after another. That's going to build a map that has that number of elements in it, a number of pairs in it, and any possible such map could possibly be reached because at each point we're choosing Y randomly. Okay, so a random function adversary has access to a random function. It can call the F procedure. It can't reinitialize it. And then the random function game is parameterized by a random function and a random function adversary. It connects the adversary to the random function, and then it initializes the random function, which in the F case, PRF case, just picks the key. Otherwise, it sets the map to be empty. And then it lets the adversary call the F procedure over and over and over again, which is either answering the adversary's questions using capital F or using this true random function map. And so what we can think of here in real ideal style is that the random function adversary is trying to tell whether it's in the real one, the PRF-based one, or the ideal one, which is this perfect randomness one. So if you're the adversary and you're calling this thing, you're thinking, as you do these experiments, which world am I in? Which world am I in? And you want to return ideally true for the real and false for the other, or vice versa. You're trying to tell them apart. Now, the goodness of F is then quantified by the absolute value of the difference between the experiment in the real world and the ideal world. So remember, the adversary is returning a Boolean judgment at the end of the day. It's returning its Boolean judgment, which is being returned as the result of the game. And so ideally here, we would like to be able to prove that the absolute value of this difference is 0. So it can't tell them apart at all. But if you think about it a little bit, this is clearly impossible without limiting how much work the random function adversary can do. So let's think about it this way. How many different functions of the form fk are there? So in the real world, well, there are 2 to the keylen of these things. So there are that many of these functions. If you think about textlen, so that's the number of bits in text, so they're going to be 2 to the textlen, 2 to the textlen distinct maps in the ideal world. That's a lot, right? So if you take textlen and maybe keylen to the 8, then there are 256 different functions that we can get in the PRF game, the real one based on what key has been chosen. But in the ideal one, as we dynamically build this map, there are 2 to the 8 to the 2 to the 8, or about 10 to the 617 different maps that could eventually be constructed. And so there's a huge difference there. And so if you're the random function adversary and you can do as much computation as you like, here's a strategy that would work. Go through all of the textlens and call the F procedure with them one after the other. Then go through all of the keys and check for each key whether that tells you those answers. And if it was in the real world, well, it will, by definition. In the ideal world, there are a vast number of possible tables that we would get. And so it's highly unlikely that we're just going to happen to be one of the ones that corresponded to one of the keys. So with enough computation, we can, with high probability, tell the difference between these 2 games. But instead, if we say that maybe that RFA, the random function adversary, is limited in how much computation it can do, then this quantity might be acceptably small. And the beauty of the EasyCrypt approach is we're not actually going to prove anything about a particular F. We're just going to use F as this black box, and we're going to use this as a formal term in our security bound for a random function adversary that's actually built out of the real adversary, according to the NCPA game and the scheme that we're using. Okay, so let me tell you just a little bit more so you can digest this before next time. What's our actual encryption scheme? We're going to use bitwise exclusive OR on text values. We're going to say that ciphertexts are pairs of text values. We'll see why in a second. Keygen will just generate a PRF key. What does encryption do? Encryption generates a random text value, and it returns as the ciphertext the pair of that text value. And what we get by taking the PRF, f of k, K for the, K for the key that we're encrypting with. We take f of k, but then we give it the text value u that was generated randomly. That gives us a text value. We exclusive OR it with the plain text. And that's the second part of the ciphertext. So ciphertexts, again, are pairs of plain text. So we generate a random u. We take f of k for the key and give it u. We get the plain text, exclusive OR that bitwise with the plain text, and this is the ciphertext. Decrypting, then what do? We take the ciphertext apart into the u and the v, and then we take the v, which is this thing, and we exclusive OR it bitwise with f of k and u. And so the idea is that these are going to cancel out. And let me show you that here. So if encryption of k and x gives us this ciphertext where u is random, when we decrypt C, we take it apart. We take this thing here and exclusive OR it bitwise with what? Well, we take the first part of the ciphertext and feed it into FK and exclusive OR with the second part of the ciphertext. And the way exclusive OR works is these will drop out and we'll be back to X. So it's a very simple scheme. If you think about it, you might be tempted to say, why do we need to include the U? Well, we need to be able to include the U because otherwise we wouldn't know what to create from the PRF. So that's why the U is included as part of the ciphertext. Okay, so we're basically done. Let me just tell you where we're going. So at the beginning of lecture 2, we'll pick up from where we got to, reviewing the material from today. But then next, considering an adversarial attack strategy against our scheme and what it tells us about what the statement should be of our security theorem. And then we'll give a high-level sketch of the proof of the theorem. So what you might do, is think, okay, so this is how encryption works. If I were the adversary, what are the pain points here? If I want to try to attack this, how can I manage to make some progress? And this is going to have something to do with 3 things. One is the quality of the capital F, this PRF, which we quantified using this metric that's here. We want this to be small. But the other thing has to do with these limits on how many times the adversary can call inc pre and inc post. And so, so when you think, if I'm the adversary, how do I try to break encryption? How do I try to do better than just winning half the time? What's your strategy? And it has something to do with the choice of these U's here. It has something to do with the quality of the PRF. Any time for a couple questions, or we still have 5 minutes? So, questions? Yes.
I said left arrow dollar sign.
Right. So this, right? Is that what you're talking about? Yeah. It's just syntax that, so this is a variable that we're assigning to. This is supposed to be a distribution over the type of the variable y. And it's just syntax for Stephen's flip, if you like. It says pick a value from that distribution and assign it to y. And why is there a dollar sign there? It's actually a parsing issue that turned out we had to disambiguate various things. And so what we ended up settling on, right. We settled on this for ordinary assignment, that for random assignment where the right side is a distribution. And so we also, so I didn't talk about this, but we also had this for procedure calls. Sorry, I could have talked about that and I forgot. So this is calling a procedure and taking the result and assigning it to that variable. This is where the right side is a distribution on bools, and we're getting a Boolean as the result. And then ordinary assignment is not on the slide, but it's like ordinary assignment. And yeah, it used to be something where the parser got confused and we settled on this. Yes?
I think you said same as Steve's flip, but I think you should be fine. Not that.
Should be.
Fine. Phone and fine. Not that.
Sure. Yes, that's true. I mean, yes. More questions? Yes. Yeah, so the question was about that default that gets returned when the limits are exceeded in enc-pre and enc-post. And well, the limits we should think of as public parameters, so the adversary knows them. And it actually, I mean, we could return a random value for the default. We could return anything. We just have, we have to return something. Good question.
If I wanted to read about the soundness of the EC-crypt proof assistant, where could I go to find that?
I will post on the Slack a link to a paper or maybe a thesis about this. A good question. Yes.
So we say that the encryption scheme is stateless. Do we just check by inspection that it's stateless, or
You can actually state that as a lemma in EasyCrypt that if you start in I guess if you start in some memory that running it gives you the same memory, so you can actually prove it. One more, and then we're not supposed to run over, so yes.
Could you explain the pseudo-random function again in terms of the real ideal parameter?
Okay. Let me see if I can really quickly do this. So what we're doing as an instance of real ideal is we're comparing this real world that's based on this capital F with whatever imperfections it has, and this ideal world that's based on perfect randomness. And so this is the thing that's perfect. This is what we would like F to be like, except it can't be as good as this. And so saying that a suitably constrained random function adversary can only tell them apart with negligible probability, that's an instance of the real ideal paradigm.
In your initial definition, you also mentioned something about trusted parties. The function I wonder if the
Yeah, I mean, so the original example involved a simulator, which this doesn't. So real ideal in general is a real world, an ideal world that's somehow more abstract or more perfect, and an adversary trying to tell them apart. And so this is an example where obviously there is no simulator. We should stop, but I'll take more questions offline.